point, I'd like to say a little bit more about subspaces, completeness, closed sets, and convergence. So here is proposition. This is basically proposition 5.3.19 in your book. I'm going to make it a little bit stronger. So let's let X be a metric space with metric D. And we're going to pick a subset of X. And remember, we can just use the same metric and turn Y into a metric space. It'll inherit all of the metric space axioms from the fact that XD is a metric space. And then we can talk about YD as a metric space. So here are two facts. If the metric space XD is complete, and remember, completeness is a property that involves the metric, which is why I'm saying XD is complete and not just X is complete. And Y is closed, viewed as a subset of the metric space XD. Then the metric space YD is also complete. And the converse is that if YD is complete, then Y is closed in XD. And this is true whether or not XD is complete or any other properties you put on it. You just need XD to be a metric space. And so any space that's complete, it's always going to be closed no matter what you put it in. So let's have some examples of what this proposition is talking about. Let's let Y be the set of all rational numbers whose square is less than 2. And then Y is closed in Q, but Q isn't complete, and you can see pretty clearly that Y is not complete. So Y is not closed in R. It has sequences that converge to plus or minus the square root of 2, for example. And conversely, let's consider the interval from 2 to 3. The interval from 2 to 3 is closed in R. So is complete. And then we can identify two, 3 with the set of all points with points in R2. Just we identify x with the point with x coordinate x and y coordinate 0, and which is also complete. So is closed in R2. So let me give you the picture of what I'm trying to get at here. So we're going to start with you can think of this line as R, or then you can take the Cartesian product of R, the real numbers with 0. They are isomorphic. You can map from one to the other. And then if you take any closed subset of this line, then it's also going to be closed in R2. So because the real numbers are complete, and so any closed subset of the real numbers is complete, we know we can we know that if we add other stuff, if we pop it into R2 or R3 or anything like that, we know it's going to still be closed. So you can't stop being closed by adding more stuff around your metric space. And this doesn't work with open sets, not even in complete metric spaces. If you take a set that's open in the real numbers, so an open interval, this is open in R, but not in R2, meaning if you grab a point in here and you draw a little ball around it, well, your ball's going to have everything, pick up everything in R, but it's not going to it's going to miss an awful lot of the stuff in R2. So closed sets in complete metric spaces, closed sets stay closed when you add other stuff, and that's not a thing open sets can do, but that is a thing that closed sets can do. I think I will leave the proof of this proposition as either a homework or exam problem. I will just give you a couple of hints, that is, a couple of lemmas that you might find useful. So here is the first lemma, and this is basically proposition 1.3.3b in metric spaces. Remember, section 1.3 is all about the real numbers, so there are some propositions in section 1.3 that are special to the real numbers, that don't carry up to general metric spaces. Anything involving a lim, superlim, inf, for example, is special to the real numbers, but there's a lot of propositions that generalize just fine. So let's let XD be a metric space. And then X is a point in X, and then we've got a sequence of points in X. And then proposition 1.3.3b says that xn converges to x if they're real numbers, if and only if xn minus x converges to 0. We don't want to subtract things in a general metric space. But we can take distances, and it turns out that xn converges to x if and only if the distance from xn to x converges to 0 in the real numbers with the usual absolute value metric let me emphasize that this is xn converging to x in the metric space xd. And the proof of that is very straightforward. You write down the two definitions of convergence, and then you use the same n's for the same epsilons. So that's not at all hard. Another lemma that is fairly straightforward. This is proposition 1.3.2 in metric spaces. And is in fact kind of important. So we're in a metric space XD again. I think I will not write that down. So the point is that a sequence, proposition 1.3.2 is that a sequence of real numbers can converge to at most one point. There are some sequences that just don't converge at all, but there aren't any sequences that somehow converge to 2 or 3 or infinitely many points simultaneously, and that's also true in metric spaces. That means that if xn is converging to x and xn is converging to y, then x equals y. And you prove it essentially by showing the distance from x to y is 0 and invoking your axioms in metric spaces. Next, I want to say one more thing about these things I've been calling balls and closed balls, or open balls and closed balls. Here is a proposition. Your book thinks it's an example, but XD be a metric space. And then we're going to pick a point in our metric space and a positive radius. Then the ball centered at x of radius r is open. And this B bar centered at x of radius r is closed. And the proof is pretty quick. Let's let y in the ball I'm claiming is open. Then rho is r minus the distance from x to y. Well, the regular ball, the open ball, means the distance from x to y is less than r, so this rho is positive. And if z is in the ball centered at y of radius rho, then the distance from z to x, just use the triangle inequality. And this is less than rho. And then the distance from x to y is, in fact, equal to rho plus r minus rho, which is r. So we have that z is in the ball centered at x of radius r, since the distance from x to z is less than r. So that means that the ball centered at y of radius rho is contained in the ball centered at x of radius r. So for every point y in the balls in bxr, there's a little ball centered at y that's in bxr. So BXR is open. Now let's prove that the other one is closed. And let's suppose that xn converges to, we've used x already, so let's suppose it converges to y. And then for any natural number n, the distance from y to x, that's less than or equal to the distance from y to xn plus the distance from xn to x, that's less than or equal to, let's leave this first one alone, but the distance from xn to x is less than or equal to r. And now xn is converging to y, so for all epsilon greater than 0, we have that there is a n with distance from y to xn being less than epsilon. So for all epsilon greater than 0, the distance from y to x is less than r plus epsilon. The only way that can be true for all positive epsilons is distance from y to x has to be less than or equal to r, and y, that's exactly what it means for y to be in this closed ball. And then so we've seen that for any convergent subsequence of what I'm claiming is the closed ball, the limit point is also in the closed ball. So that means that our closed ball is in fact closed. Couple of other facts I want to mention, couple of other sets that are always open and closed. This is a little bit non-intuitive, but follows straight from the definitions. You'd pick any metric space then X and the empty set are both they are both open sets in XD and also closed sets in the metric space XD. And this is one of those things that's so simple it's really hard to explain. It's sort of like proving that a constant function is a function. So to prove that X is open, we're going to pick a point X in X. Then the ball centered at X of radius 1. Doesn't have to be 1, can be in your favorite positive numbers. That's the set of all points Y and X such that the distance from X to Y is less than 1. That is obviously a subset of X. So every point in X, you can put a ball around it that's also in X. So X is open. And then we're going to pick a sequence in X. So we pick a subset of the thing we're trying to prove is closed, which is X, that converges to some point X in our metric space. And this is a little confusing. We're thinking of X both as a subset of X and of the entire metric space. But then our target point is always obviously going to be in our thing we're trying to claim is closed. So X is closed. And then the empty set is open because its complement is closed. You can also prove the empty set so it's closed because X is open. And vice versa. It is also possible to prove directly that the empty set is closed and open. The definitions are a little bit confusing because, for example, open set. For all points in the empty set, there's a ball around it in the empty set. That is technically vacuously true because there aren't any points in the empty set. So vacuously, none of them have whatever property you want. And similarly for this convergent sequences characterization of closed sets. But I think that's even more confusing than proving that the whole space is open and closed, so I will not write that out. Now we are going to talk about closures, interiors, and boundaries. That is, we are going to start with a set in a metric space, and we're going to define three other sets called the closure, the interior, and the boundary of that set. And then we're going to talk a little bit about how those relate to the set and each other. So we start with a metric space. And a subset of that metric space. So this subset might be open, it might be closed, it might be not. Very rarely will it be both. And then we define the interior of A is often written like this: int A or int of A. That's the union of, you take all the open sets. I'm going to write this as G in O of A, where O of A, I'm going to call that the set of all open subsets of A. And the closure of A is written like this, just CLA. That's the intersection of all sets F in, let's call it C of A, where C of A is the set of all F subsets of F of X such that A is a subset of F and F is closed. And then the boundary of A is written like this with a partial symbol. That is the closure, everything that's in the closure but is not in the interior. And let's have an example, a nice pictorial example of something like this. Let's take this as our region A. So A is the set of all points x1, x2 in R2 such that our x1 coordinate is positive and x1 squared plus x2 squared is less than or equal to 1. And then how do we get the interior of A? So we're going to zoom in on it. We take every point in A where x squared plus y squared is less than 1. You can draw a little ball around that point, and that little ball is open. So we fill in A with all of these little balls. And then the interior of A is the union of that. It's this half circle with everything that's not on the edge. And then the closure of A we're going to take all the closed sets that contain this thing, and then we just shrink them down as small as we can. And at the end of the day, the closure is this half circle with all the bits on the edge. And we're trying to match this up with our intuitive notions of what the boundary is. Everyone wants the boundary of this set, the boundary of A, to be this half circle, just this big D shape, nothing on the inside, nothing on the outside. And in fact, it turns out from our definitions, that's exactly what the closure comes out as. And let's write out some obvious facts about the closure, things that are straightforward enough that I don't think they need a proof. First off, let's notice that the empty set is one of the open subsets of A, and the entire metric space is one of the closed supersets of A. So the interior and the closure, they're the union and intersection of at least one set. So this is AI went to so much trouble to point out that the empty set is always open and the whole space is always closed. Here's another fact, is that the interior of A is a subset of A. The interior of A is a union, but everything you're unioning up is a subset of A. Therefore, their union has to be a subset of A. There can't be anything that's not in A. And then your closure is an intersection, but everything, every set you take an intersection of contains all of A. So it is, so you get, so necessarily the closure contains A. And here is another fact, is that the interior of A is open. And the closure of A, unsurprisingly based on the name, is closed. And that just follows from Proposition 5.3.2, which says that you can take the union of as many open sets as you want and you get an open set. You can take the intersection of as many closed sets as you want, you get a closed set. You're usually going to have infinitely many open subsets of A, probably uncountably many open subsets, but that's okay. You can still take arbitrary unions. Another thing to point out that follows from the definition is that interior of A is the largest open subset of A. If G is a subset of A and G is open, then G is also a subset of the interior of A. So certainly whatever you think bigger means for sets, if you're a subset, the subset is smaller, the superset is bigger. And the closure, on the other hand, is the smallest closed superset. And these two facts are just following from the definition. If G is an open subset of A, it's one of the things we took the union of to get the interior, so it must be a subset of the interior. If F is a closed superset, it must be one of the things we took the intersection of to get the closure, so certainly it must contain the closure. In particular, if A is either open or closed, we can say that A is equal to either the closure or the interior. And that is, in fact, a proposition in your book. It's not a terribly difficult proposition. So part A is open if and only if A is equal to the interior of A and A is closed if and only if it's equal to the closure. And the proof is pretty straightforward. We're going to use the above facts. So if A is closed, then A is one of the closed sets containing A. So closure of A, which remember is equal to the intersection of all the closed sets containing A. It's a subset of any particular one of them, so it's a subset of A, and we have A is a subset of the closure of A for all A. So if A is closed, then we have these two inclusions. A is equal to the closure of A. And if A is open, then, well, A is a subset of itself. So it's one of the open subsets of A. So A is a subset of the unions of the open subsets of A. It's one of the things you unioned up, which is the interior of A. But that is a subset of A for all A. We saw that the interior of a set is always inside of the set, so A is equal to the interior of A if A is open. And then the interior of A is always open. That was one of our facts above, following from proposition 5.3.2. Closure of A is always closed. So the reverse implications are pretty trivial. If A equals interior of A, then A is open. And if A is equal to the closure of A, then A is closed. And that completes the proof. I would like to now talk a little bit about interiors and complements. So remember, the complement of a set, we write that as X minus A. That's the set of all points that are in X, that are in, that are not in A. And next, we're going to prove something about the interior and closure of the complement and how that relates to the interior and closure of the set. So we start with a metric space. And a subset. And then we can write this in about 3 different ways. So the proof is pretty similar. X minus the closure of A. That's the same thing as the interior of the complement of A. So everything that you want to think of as being inside the complement is precisely the stuff that's not in the closure of A. And similarly, the complement of the interior is the closure of the complement. And the boundary of A is everything that's in the closure of both A and its complement. So you can think of the closure of A as all the points that are close to A. They're so close to A that they're in all the closed sets containing A. The interior of A is then the points that aren't in the closure of the complement. It's all the points that are far away from the complement. And the boundary is the things that are in both closures that are close to A and also close to its complement. And let's prove this. So remember that the set C of A is the set of all F such that A is a subset of F, it's a subset of X, and F is closed. But notice that if A is a subset of X, that means the complement of A is contains the complement of F. If everything is in A is also in F, that means that everything that's not in F has to not be in A. This is De Morgan's laws. And also remember that F is closed if and only if its complement is open. So we'll write that as X minus F is open. But then now we're looking at all the open subsets of X minus A. So I'm going to replace F by X minus G. So F is X minus G such that G is a subset of X minus A. G is open. So C of A is the complement of everything in O of X minus A. And then, and similarly, the open subsets of A are the complements of the closed supersets of X minus A. You can get that just by replacing A by X minus A in the above equation. So the interior of X minus A, that's the union of all open subsets of X minus A. That's the unions of all the X minus F's such that F is in C of A. And if you remember De Morgan's laws, when you use complements, it flips unions into intersections. And that is just X minus the closure of A. And then exactly the same argument works for the closure. And then the result for the boundary. I've defined the boundary as the closure minus the interior. We can write that as the closure of A intersect everything except the interior, and then we can just use the above results. And that is all there is to that.